This document is related to the design of a transradial hand prosthesis mechanisms and the synthesis of a Toronto mechanisms. TIAN is a mechanism composed of 6 linked bars as it is shown in next figure. The first design was proposed by Nikolai Dichet in 1999. This design was proposed as a finger mechanism for a hand prosthesis. The connection between the links are shown in broken and curved lines as the next figure, and all the mechanisms moves describe the trajectory how it is shown in second figure. The problem of synthesis in TN implies to set the mechanism from initial and standard position and assure that the mechanism finally arrives to contracted end position. The main purpose of the mechanism is to simulate a finger movement in only a degree of freedom. The development of the synthesis in this mechanism requires the solution of a great amount of equations, as the designer says. After many iterations, and with the aid of working model to this software, satisfactory cinematic and dynamics of the finger were achieved. Later, in 2015, was proposed a document entitled Diseño mecánico de prótesis de mano multidedo, where the author tried to solve the synthesis of the Toronto mechanism, beginning with a geometric inexact solution, and finally proposed a computational exact solution, but computationally expansive. To solve the initial problem, here it is proposed two solutions. The first proposal is a vector solution, and finally was proposed a geometric and exact solution to synthesis of Toronto mechanism problem. The geometric data was collected from measurements of the left hand in a transradial hand amputated patient. Since the Tn is the connection of two mechanisms of 4 bars each one, consequently, here is proposed the equation related in synthesis of a 4-bar mechanism known as Freudenstein's equations. In synthesis of 4-bar mechanisms, it is necessary to assure a controlled movement of it from an initial to final position, how it is shown in figure 4. Here you can see how the Freudenstein's equation number 1 and number 2 can be translated in a final and vector equation 23. To prove validation of equation 23 had been developed a simulation in a graphical software AutoCAD with parametric tool, simulating a 4-bar mechanism, how it is shown in figure 6, for two positions and getting the coordinates of x and bars. Finally, it has been developed a MATLAB algorithm to prove validation in graphical values of equation 23. To prove vector equation in TM, it was considered the following assumption. First, proximal phalanx rotates alpha 1 degrees. Next, medial phalanx rotates alpha 1 plus alpha 2 degrees or alpha 2 degrees relative proximal phalanx. And finally, distal phalanx rotates alpha 1 plus alpha 2 plus alpha 3 degrees or alpha 3 degrees relative medial phalanx to see figure 7. In consequence, the first mechanism must accomplish the equation 24, and the second mechanism must accomplish the following equation 25. To prove validation of equations 24 and 25, have been developed a graphical simulation in AutoCAD software employing the parametric tool to simulate the connection between components to get the coordinates as points A, B, C, D, E, F, and G, how is shown in figure 14 to a standard and flexed position to the mechanism. Finally, to prove validation of equations 24 and 25, the coordinates obtained have been proved in a MATLAB algorithm shown here. Finally, here is proposed a geometric solution of synthesis of Toronto mechanism, how it is shown. First, it is recommended to get real measurement of finger position starting with applying of the finger profile. See figure 10, where points A, C, and E are articulation points of three phalanges. Next, it is required to trace a line from D to D' and draw a mediatrix line to the D' line, and after draw a point H that passes through mediatrix near to articulation point A to see figure 11. Just now trace a broken line HDK that will define the first connector bar. See figure 12. The K point is any point outer to CDA phalange. Now it is required a copy of HDK broken line that passes through HD' K' points to see figure 13. Draw line K and its mediatrix 2, and after draw a copy of EFG phalange in contracted position relative CED phalanges and draw FF' line and its mediatrix 3. After find the intersection between mediatrix 2 and mediatrix 3 in point M to see figure 14. Finally, the broken lines E and F and DMP have the same opening angle epsilon. At last, the broken line XDP and the PF line define the two connector bars of the Toronto mechanisms. To prove the validation of the geometric solution, additionally, these results were employed to build a real mechanism of radial prosthesis, and exclusively was designed and built an index finger of the prosthesis to see figure 16. The construction of the finger prosthesis was developed with collaboration of two engineering students of Mechanical Engineering School at the Industrial University of Santander to get their project degree. Considering that geometric exact solution, it is an easy way to solve the synthesis of Toronto mechanisms. To consider an optimum solution should be considered in further words due to 2 degree of freedom make possible expose infinite combinations to solve this problem. To design a computational tool that considers the two vector expression of Frank-Denn's equation and rotational transformation surely will lead to design an efficient and easy software to solve the synthesis of Toronto mechanisms.